also have the pleasure of working with him on a daily basis. So Chris is a program manager at IARPA. One of his main programs is the Odin Program on biometric presentation attack detection. So I'll let him talk about that program. He comes to IARPA through Oak Ridge National Lab. So thank you, Chris, for coming, and
thanks, Nathan.
Get you out of here.
I also have the privilege of working with Nathan and these guys. I would highly encourage it if you ever had the chance to collaborate with any of them. Between Snow and the fact that most of you probably know what IARPA is, I'm going to skip right through that and move straight on to the Odin program. So yesterday I had talked about prize challenges, which is one of the ways that we get things done at IARPA. The other way is through our large programs. So typically these programs consist of 4 teams, although we tend to reduce the number of teams as phases go on. In this case, this is a 4-year program, 3 phases. Odin is focused on presentation attack detection, specifically within the face, finger, and iris domain. And for those of you unfamiliar with what a presentation attack is, some people will call it spoofs. But, you know, presentation attack has some advantages in terminology. Really what we're focusing on here, oh, and it doesn't show up on the screen. Oh, there we go. All right, so what we're focusing on when we say presentation attacks are things that occur between the sensor and the biometric sample itself. So certainly the cybersecurity guys can talk about, you know, all the stuff going on down here in the electronics portion, and I'm not suggesting that's not important, but that's not the computer vision, you know, relevant piece. So we don't look at that. These spoofs are things like you can see fingerprint overlays, prosthetic eyes, face masks, things like that. Within Odin, we're focused on a variety of different use cases. This is actually one of the more challenging aspects of the program because it means that an individual performer's solution may be good for some use cases, but not others. So as an example, we've got low security cyber. This is things like your phone, right? And then we've got high security facility access. These are things like securing nuclear weapons. And, you know, we're at an application conference here, right? Those are not the same application. You know, yes, it would be great if we had a magic bullet solution that worked across all of these different use cases, but in all likelihood, that doesn't exist. And while I am a program manager who loves to write requirements, and I'm confident I could write the requirement of the magic bullet solution, I'm also a scientist and engineer, and I don't think you could do it. So within these different use cases, we look at, you know, what's your false alarm rate, because certainly you can make your systems very secure. You can crank your knob on your rock curve and, you know, make sure that the bad guys never get through, but what are you doing to the good guys, right? If you're looking at an airport use case, if you even have a 1% false alarm rate, that's going to kill you. So, you know, we're trying to have realistic, you know, items here. I'm also confident that you could have a GC mass spectrometer, an electron microscope, and a variety of other scientific instruments that would do a great job at presentation attack detection. That's also not a realistic solution. So cost, time, things like that come into play. And finally, we have to have backwards compatibility, right? While this is fundamentally not a biometric matching program, if the systems that we produce are great, you know, presentation attack detection systems and can't capture a biometric sample to save their life, that's kind of a pointless solution. So fundamentally, all of my performer teams are focused on building this blue box in the middle, right? That means they need to come up with the sensor electronics and pad algorithms package that is going to take in one of 3 different things that we're going to throw at them. It'll either be a true biometric, so no presentation attack, it'll be a known presentation attack, or it'll be an unknown presentation attack. Now the unknown is actually, to me, particularly important within this program because all too often in the cybersecurity realm, what we see is people learn the signature of an attack and then assume they're safe simply by blocking that signature from attacking them. This is why when you hear, you know, zero-day exploits and things like that, that's such a big deal, because if it's a 0-day and they've never seen it before, it's guaranteed to get through. So what we're trying to do is push everyone to build intelligent systems that can anticipate when an attack is occurring, even if it hasn't seen it before. So once the system takes in this information, it has to give us a backwards compatible legacy biometric sample. Then it has to identify if it thinks it's a known presentation attack or an unknown presentation attack. And because we're good scientists and engineers, some of the teams output additional information, right? That could be a 3D fingerprint, it could be all sorts of things that could be useful in the future or for a variety of other purposes. We have 4 primes within this program: Michigan State University, Crossmatch, USC ISI, and SRI, and they all have various fabulous subcontractors as well. Our test and evaluation team is led by John Hopkins APL with NIST in support. NIST's primary role is in looking at the backwards compatibility of the match sample. The far majority of the work for the T&E team is we are actually having all of these teams bring their hardware to a common physical location and having several hundred to a couple thousand, depending upon which phase we're in, subjects go through each sensor. So similar to the theme yesterday that we're releasing data, at some point we'll be releasing data on this program as well that you guys can all play around with. But, so we're making sure that the same person and the same attack is seen in all the systems so we can do a more honest comparison between different approaches. Now, different teams have taken different approaches that, as I mentioned, may lend themselves toward different use cases. MSU's approach is much heavier on the software. So, for example, they're using deep learning and convolutional neural nets to try and analyze legacy optical fingerprint images for pad purposes, right? So this is both fascinating and terrifying to me because it's a really cool idea, right? If you could just look at the existing samples we're capturing today and detect pad, that would, one, mean we're backwards compatible. We could probably comb through all of the existing databases we have and find out any attacks that are ongoing, and it would be a much easier rollout. I'm also a little nervous about this because, while I love deep learning, I run the Janus program, we don't understand what it's queuing on. So, when they show results, which are great, you can see here, you can see here, they're using a minutia patchwork-based CNN analysis of these conventional fingerprints. The green fingerprint is, these green patches means it thinks it's genuine, the red is false, and it works pretty well. But what is it queuing on? Nobody knows. And so that makes me a little nervous. The good news is we've got independent testing we're going to be doing, so we're going to figure out if there's, how well it's working. Similarly, in MSU's case, they're doing interesting things with iris and face. They are bringing in some different modalities of data, but primarily they're lighter on the novel sensors. Crossmatch is, if you're unfamiliar with them, is a private biometric company. It's actually really fun for me to get a true company that makes this stuff into our research program because they're able to do things that the other performers can't, right? And the converse is true as well. So this is not to say private companies are always better. But so they are actually fabricating with one of their suppliers a combined optical capacitive fingerprint sensor. So they literally are making a brand new sensor, laying new silicone, where each pixel has both optical and electrical sensitivity to it, right? So it's really cool from a pad perspective because it means, in theory, you're going to be able to do both of those tests together, and because the data is aligned, going to the theme of some of the things we're doing here, you can probably do cool things that you couldn't do if you just had the two side by side, right? Because you've got the data perfectly aligned. So that's going to be pretty cool. They're also doing some rather interesting 3D structured light iris capture and fingerprint capture. As an example of why 3D could be really important for iris, you can tell the shape of a contact lens, right? It's curved, it goes out, right? Whereas the iris itself is actually flat. So if you're looking at the shape of the sample you're capturing and it's not flat, it's not authentic, right? Now you can say, oh, well, hold on, then I can just hold up a sheet of paper. But you can analyze the other 3D around it as well. So it's not just that the iris is flat, you can look at other things too. So there's some really interesting things going on there as well. USC ISI, they and SRI both have relatively sensor-heavy approaches, although SRI has even more sensors involved in what they're doing. ISI's primary unique sensor is laser speckle contrast imaging. So basically they shine a laser at stuff and they look at how the laser behaves. And they would claim that they can see things like blood flow, right? Because, let's see, it's kind of hard to tell because it's relatively little here. But if you're looking at this imagery, this is imagery of fingers, and they can detect that blood is moving through the fingers. And in theory, you could do that for face, and you could do that for iris as well. So, it'd be pretty challenging to try and spoof that particular feature. Now, they're also looking at a variety of different modalities for things like face. So down here, you can see they're looking at conventional color, depth, various multispectral data, and trying to figure out how to merge that all together with machine learning to detect when attacks are happening. So that's very similar to some of the stuff that these guys were talking about earlier, where perhaps an NIR it's harder to defeat, right? So USC ISI has a very interesting mixture of sensors involved. SRI has taken what I call the kitchen sink approach to this problem, and that they have thrown every sensor they think might be helpful at it. In their original plan, they actually had a scale. You were going to be standing on a scale as a part of how this whole process worked. So now, their plan includes narrowing this down throughout the program. So this is not to suggest that they're planning on ending with quite all of the sensors they have today. But they are certainly sensor heavy. They're also very focused on how to capture, and when I say biometrics here, what I mean is physiology, right? So, heart rate, breathing rate, things like that, right? So they're capturing other biometrics and trying to correlate them across all of the different samples. So their theory is that it's going to be harder to produce a biometric presentation attack that can mimic all of this at the same time, right? So not just does it have a fingerprint, not just does it have a heartbeat, does it have blood flow, but does the heartbeat and blood flow in the finger match the heartbeat and blood flow in the iris, match the heartbeat and blood flow in the face, right? They also have a rather unique sensor, not necessarily in that the sensor technology is unique, but in how they're doing it in the form of optical coherence tomography. So one of their subcontractors is a startup focused on producing low-cost OCTs. If you're unfamiliar with optical coherence tomography, you can see an image of what it looks like down here. It's kind of like ultrasound, but using light. So the fact that it uses light and it's semi-penetrating means they can look at things like iris and they don't have to physically touch it, right? And the theory is you can look at multiple layers of the fingerprint, similar to how Luminime would claim to work, although I'm not sure it actually does work the way they claim it, and be able to detect attacks there. Now, the startup's whole pitch in life, though, is they think that they've got a roadmap to producing low-cost OCTs. So today, if you want an OCT, you can get one. It's about $70,000, give or take 20 grand. Well, on the low end, 20 grand, you can probably spend as much as you want on a fancy one. But, from a company like Thor Labs, right? The startup believes they can use conventional products built into things like DVD drives to actually get the unit cost down to the single dollar, right? The theory is they can have OCTs that are going to go into cell phones and all sorts of fun things like that. So within each phase of Odin, we actually kind of change our focus from a T&E perspective. In phase one, we're really just kind of focused on everyone building their system and fundamentally getting something to work. And then in phase 2 and 3, we really further push the boundaries on some of this unknown detection. I really think the unknown is what's going to wind up being fascinating about this program, in that how are these systems going to respond to things that they've never seen before, right, or didn't anticipate. I briefly touched on this earlier, but what we do for our testing is we actually have real people, right, a lot of them, because we need a lot of data to get the statistics we want, go through each sensor. So not only do they go through the different performer sensors, they go through baseline technology. So, obviously we have to make sure that how we're doing this is as good or better as it happens today. The commercial technology has actually been advancing pretty impressively in terms of its presentation attack capabilities in the last year and a half or 2 years. The private sector really is starting to pay attention to this. Now, the flip side is where the private sector isn't doing a very good job is really thinking about their false alarm rates. So they're very happy to be able to just say, oh, we can detect all presentation attacks. But then if you try and poke them on, well, how often are you annoying your legitimate users, they really don't want to say, whether it's because they don't know or they just don't want to say, isn't clear. But I can tell you that anecdotally, we've had an iris sensor, for example, that out of a relatively small group of the core testing staff who use it, 2 of whom are consistently rejected as having fake eyes. And I promise you, in this case, they are not fake eyes, they're real eyes. So, I think the real challenge here is maintaining the performance we want under the false alarm rates that make sense. And thus far, the private sector is pretty far from solving that problem. Within the program, we have both metrics and constraints. Really, our only metrics here are your true detect rate at a fixed false alarm rate. A lot of people, when they see this, yell at me and go, Chris, the ROC curve matters. Don't pick fixed points on the ROC curve. I agree with you. The catch is we need ways of evaluating our progress, whether we're meeting our goals. And it's pretty hard to kind of look at a ROC curve and try and say if you're meeting your goal. I mean, you can start looking at things like your end of the curve and stuff like that. But as you do that, you tend to not always measure what you really care about, right? Really low false alarms, things like that. So we have picked specific points. We're also looking at capturing a lot of data. I think the next slide gives you a hint on number of subjects. Next one. All right, I'll just skip ahead. So you can see we're planning on capturing a lot of data at each test. We have both what we call self-tests and government tests. So the self-tests are things that the performers do on their own. They recruit their own subjects, and they basically self-report how they're doing. Now, don't get me wrong, I don't think any of the teams in this are dishonest and would intentionally lie to us, but everyone can implement their self-tests subtly differently, right, in ways that can create problems. If nothing else, the fact that you have fundamentally different subject pools at each performer location could impact it. So where you see the S, that's a self-test in our plan, and where you see the G, that's the government test. So in the government test, what we're doing is we are actually having all of the teams come to our location in DC and go ahead and capture data so that we really can, directly compare them. As you look at this, you'll see a difference between the number of presentation attack trials and true attempts for the scientists in the room, or the statisticians more accurately. That's because trying to make sure we're hitting the low false alarm rates we need dictates that you wind up needing a lot more data of your true subjects. So we also have a taxonomy that we use within the program to talk about how all of this different stuff works. It's based upon the ISO standard, although we're not unwilling to vary from the ISO standard where we think it's necessary. And so within that, we have developed a set of presentation attack recipes. So one of the challenges I had in running this program is we want to make sure that we are catching bad guys, not helping them. And the minute you start talking about, hey, we've made a new attack to defeat a system, right, you run the risk that you're helping the bad guys more than you're helping them. The catch is we need attacks, because if we don't test any attacks within the program, right, what's the point? Right? We can say, oh, it's going to work, just trust us. We just haven't tested it yet. So that's a pretty bad plan. So what we've done is we've pulled from attacks that are already out in the open, right? Chaos Computer Club, plenty of universities and private citizens have developed various attacks out there. And what we have done is we've put them all together into what we call our recipe cards and our index of recipes. This is an example of an actual recipe card that we use. This really serves two purposes. The first is from a scientific perspective, it allows us to more accurately control and compare attacks. So that if Michigan State says we're doing a Plato-based fingerprint attack and SSRI says that, we can have some degree of confidence that they made it in relatively the same way. The second is that security aspect, because we're really trying to make sure that we're not adding to the attack pool that the bad guys are going to be using. Here's another example of one as well. You can see, this is a different recipe card example, but this just gives you an example of how it may perform. Worth noting is long-term, we're working on figuring out how to share our recipe index with qualified researchers. The challenge is what that means. So fundamentally, I have no problem with researchers who are trying to help us catch bad guys too, sharing our recipes, right? It's pretty important from a scientific perspective, but we don't want to just post on the web and give it to anybody. So we're working on criteria to figure out how to share that. So if you are interested in getting a hold of our recipes so you can figure out how to make PAs in a consistent manner for testing, stand by, we're working on it. This slide also just highlights that you can set up different security levels and things like that for fingerprint spoofing. This is just another example of a different recipe that we do. This particular one is based upon PCB molds to make various fingerprint overlays, and it gives you detailed instructions on how to do that. And then you can begin to look at testing and see what that does. For example, for this particular PA, if you were to use it on something like the Lumidyme is fairly effective at detecting it. And we also, of course, look at, how does it look from a quality perspective, things like NFIQ and stuff like that. But so we're going to be running these PAs through all of our various sensors. So where are we in test and evaluation? We just completed our first self-test. And we captured a ton of data. We've been, looking at a variety of different attack types for face, finger, and iris. But, another challenge I think that this community has is trying to understand presentation attack complexity, because there's really a difference in detecting, say, a printed sheet of paper and some PCB mold, complicated fingerprint overlay. The challenge is, what do we mean when we say complexity, right? This is kind of a nebulous concept. So what we're trying to do within the program is develop kind of a way of analyzing complexity with a simple 5-point scale, because, the more it can be a discrete value in between those, but, binning it so that you can talk about, okay, this set of systems is really good at the simple attacks and doesn't do as good at the more complex attacks. With the idea being that depending upon your application, going back to us being an applications conference, you may want a different solution, right? Cell phones may be fine only handling, low or medium attacks, whereas if I'm protecting nuclear weapons, I'd like to be pretty confident, that it's a high security solution. So what we've done is come up with different factors to evaluate the materials that go into it, how easily available they are, what kind of lab requirements do you need, how much skill do you need, how long does it take, and how hard is it to use. So at the moment, we are basically just evaluating in our expert opinions these different categories and then weighting it together to evaluate attacks. I will briefly mention, that we also have the Janus program. I talked in depth about prize challenges yesterday, but we also have the Janus program, which is focused on unconstrained face recognition that we do as well. That program has been very effective at leveraging all the advancements in deep learning. When we started the program, our goals were so aggressive, most people thought we weren't going to hit them, but we've actually made them 2 orders of magnitude harder by the end of the program. So we were meanies and we moved the goalpost on all of the performer teams, but they're still doing great and hitting their goals. So that's going really well. With that said, I have time for a question or two, if anybody has any. It's okay if you don't. That just lets me hit the shuttle quicker.
I'm not going to let you get out of here that easy. I do have a quick question / hoping you can make a comment. So for the researchers in the room, I know this is a presentation attack detection program, but there's a ton of data being collected. Can you comment? And you mentioned that it's going to be available and shared. Can you comment at all how much the performers are actually focusing on using that data for recognition and whether there are opportunities there for others to get into that space?
So fundamentally, this is not a recognition program. So the requirement that the performers have is to ensure that the data they're capturing is backwards compatible. So if you're capturing a 3D fingerprint, you need to make sure it will match conventional flat fingerprints. But the goal is not to improve recognition. So not that isn't important, that's just not the goal of the program. So none of the performer teams should be spending my money on that unless they're not as good as we are today. And so there certainly is ample opportunity for other people to use the data for that purpose. We're also collecting a variety of baseline data. As long as we're getting the large volume of people going through that we are, we're capturing conventional samples that certainly, if you're solely interested in biometric recognition, you can use. A few of our government partners have also asked, and we are letting them jump in to collect data as well. Sean, I hope you don't mind me mentioning this, but Sean is planning on capturing polarimetric thermal data, right? As long as we're collecting this, and I believe it's Sean's intent to release that data to the public as well. So there will certainly be data that's useful beyond presentation attack detection purposes available.
Okay, great. Oh, got another question.
All right, last question.
So if we have other sensors, would it be possible to get other sensors added to your collection if we can provide?
So you would need, in theory it might be. Few caveats. One, IRBs are a pain in the ass, right? And so that means you might not necessarily get into the next round of testing we're doing, but we're doing testing over the next several years. And the final caveat being that you need a government sponsor. So you either need to convince me it's in the government's interest to capture this additional sensor of data, or you need some other govy you work with to call me up and ask me to do it on their behalf. But yes, fundamentally, it's possible. Oh, you do have to capture the data yourself. I will give you a booth and access to subjects. I am not agreeing to man your sensor, okay? Me personally or my collective team, right? So the theory is if you're coming to me and saying you want data on polarimetric thermal, right, that you want it badly enough that you are going to sit there for however long it takes while we're capturing data, and capture it yourself. All right, thank you, everybody.
We're going to let Chris get